Welcome to the code exercises for chapter 8. This chapter is all about probability theory. Let's begin with exercise 1, which is all about the units of the PDF, the probability distribution function that is outputted by various functions that come in the SciPy library. Okay, and so here I say that this exercise and also the next one is all about the normal distribution, the Gaussian distribution, but the principles that you will learn here, so basically the concepts in this and the following exercise apply to all of the distribution functions, not just the normal distribution. Okay, before showing you that text. So to start with, create a PDF, a probability distribution function, which is a discrete estimate. It's a computer digitized estimate of a probability density function. So create a PDF of a normal distribution using an x-axis grid of -4 to +4 in 400 steps. Now, if this is a true probability function, then the sum over all probability values must equal 1. So check this empirically. Okay, so there's a little bit more to this exercise, but first I want to switch to Python and start working on this part, and let's see what happens when we sum all of the probability values in the PDF. Okay, so here I'm creating the x-axis grid spacing, -4 to +4 in 400 steps, and here I use stats.norm.pdf to create this variable PDF4. I'm calling this 4 because we're actually going to be using this variable again in the next exercise. So if you haven't yet gone through the next exercise, that's totally fine, but it will be handy just to have these as separate variables. Okay, so again, the sum, if this thing really is a probability distribution function, then the sum over all of these probability values must equal 1. That's part of the definition of a probability function. And surprise, surprise, it's actually not equal to 1. Not even close. It's, almost 50, which is a lot larger than 1. Okay, so let me now go back to the text and we will figure out what is going on here. Okay, so here we've already empirically discovered that the sum of all of the probability values is much larger than 1, meaning it's not a true probability function. And here is the deal. We actually just need to normalize it. It's not so difficult. So basically, the definition that all the probability values must sum to 1 comes from this formal expression here where we take the integral over all of the probability values dx. We have to multiply by dx. And that is the key that is actually missing from our code. So what we've done in the code is sum over all the values of p, of the output of this probability distribution function. And well, we didn't really formally integrate. We just summed, but that is like the digital version, the discrete version of the integral. So what we did was sum all of these probability values. We didn't actually scale by dx. And what is dx? Well, when you have an integral, you're working with calculus. Dx is like some tiny, tiny number. It's an infinitesimal, say infinitesimal, or some debate in calculus about whether we're allowed to use that term. But anyway, it's a tiny, tiny, tiny number. But in our case, dx is the discretization of the x-axis grid spacing. So we went from -4 to +4 in 400 steps. So whatever is the distance between two successive x values, that is our dx. So we need to normalize by that dx. Okay, so now I will switch back to Python and I'll show you that normalization. Normalization is really simple. So here I call this variable PDF for n. The n is for normalized. And all I'm doing is multiplying by the difference between any two successive values of x. So this is going to give me dx. It doesn't necessarily need to be the second element minus the first element. It can be the last element minus the second to last element. Doesn't matter which element you pick. Any two successive elements will have exactly the same spacing because of how I defined this function. So we multiply by dx, and then we can sum again, and we see that we get a value of 1. So in fact, when we normalize appropriately, the output of the stats.norm.pdf function is really a probability function. Here we are with exercise 2. of chapter 8. This is following up from the previous exercise. So make sure you have done the previous exercise, exercise 1, before starting exercise 2 here. And in fact, you're going to copy and paste a lot of the same code. So so there's a couple of things to do in this exercise, but we're going to start by repeating exactly the same code in the previous exercise, but instead of going from -4 to +4 in 400 steps, now in exercise 2, we're going to go from -2 to +2 in 300 steps. And then again, compute the sum over the probability values or the output values of the stats.norm function. Okay, so you can already see what's going to happen. But before moving on, I'm going to switch to Python, work through this, and have a small discussion. And then I'll come back and we'll go to the rest of exercise 2. So you can see here that all of this code is pretty much identical to the code from the previous exercise, except that I changed the x-axis grid spacing here. So -2 to +2 in 300 steps. And then I changed the variable name. So this is x2, PDF2, but the normalization is exactly the same. Now, in the previous exercise, we discovered that the sum over the normalized PDF was exactly 1. It was 1.000. But now it is not 1.000. It is 0.955. Now maybe you think, okay, Mike made a coding error somewhere. There's something wrong here. But, I can change this. I can go back to how it was before. It was -4 to +4 in 400 steps. And here we do get 1. Okay, so let me undo all of that. So now we are going to try another normalization that is going to absolutely guarantee that the sum over all of the elements in the PDF is going to be 1. And the way that we are going to do this is, instead of scaling by dx, just divide the output of stats.norm.pdf by its empirical sum. So whatever the sum happens to be, remember in the previous exercise, we discovered that the sum of the non-normalized PDF was 49.85 something. It was somewhere around 50. Divide by that value. So just whatever the sum is, divide by the sum. That will trivially force the function to sum to 1. Okay, and here I say this is called a unit summation normalization. Okay, and then plot the 3 PDFs. And I'll show this graph. I'll talk about this graph in Python when I create it. Okay, so here we have a little bit of extra code. I take the output of PDF here. This is not the normalized by dx output. This is just the raw output, which we know is not going to sum to 1. And I divide it by its sum. And when you do this, that is, as I mentioned, it's called unit sum normalization. It is trivially forcing the sum to be 1. And we see that here. Okay, notice also these are all different variable names. So I have PDF4. From the previous exercise, I have PDF2N and PDF2U. Okay, so then I'm just going to plot them, very simple. And let's see. So here we see this is the x-axis grid spacing here. These are the 3 different PDFs that we have normalized in different ways. And they all look a little bit different from each other. I mean, they all have the same shape, obviously, but the heights are different, obviously the boundaries here are different because these 2 functions are defined as going from -2 to +2. So what is going on here? What is the deal with all of these normalizations? Let me start by discussing the dx normalization here. So the dashed line and the dotted line. Now up here, I said, and I explained, I hope it was pretty clear in the previous video, that we need to scale by dx because that is, that comes from the math. It comes from the integration. That we have a dx term. But why did that only work for the previous exercise and it didn't work for this exercise? Well, the key is that we have a restricted range. So in theory, the probability integration goes from -infinity to +infinity. But here we are not going from -infinity to +infinity. We have a much more restricted range. Now, once you get far away from 0, negative or positive, you can see that these values, it looks like they're 0. They are technically not 0. They are above 0, but they're so incredibly close to 0 that they are tiny, tiny, tiny. So, all of the sum of the probability density function from minus infinity to minus 4 is really, really, really tiny. There's extremely little area past minus 4. But you can see this is really obvious. From minus 2 to minus 4, I mean, that's still a relatively small area, but it's not insignificant. In fact, the amount of area that we are missing here by cutting off the boundary is somewhere around 0.045 approximately, rounded. So it's small, but we are really missing something. And that explains this value. And in fact, if we go back up here, back to exercise 1, you can see in the instructions for this exercise, I said only print out the first 3 digits after the decimal point. And if we were to do, let's say, the first 9 digits, so here you see this is 1.000, but it turns out that that is also rounding. So now we can see going from minus 4 to plus 4, we're still not really getting to a sum of 1. We're getting to a sum of 0.999939305. And, it's going to keep going out there. So again, the difference between this number and 1 is basically all of the area that we are missing between minus infinity and minus 4, and between plus 4 and plus infinity. Okay, and then that's why this normalization is it's like mathematically still correct, but it just doesn't cover the whole range. It doesn't give us enough numerical distance to really get close to 1. Okay, and then the unit norm obviously forces it to be unit norm, so it's going to shift up a little bit. And if you like, one thing you can try to do, this is not in the exercises, but it's just a small addition, is to apply this unit normalization to the PDF from exercise 1. So this one up here, and then you can add a 4th line, and you will see, these two are different from each other. When you normalize to unit sum, then you will see that one looks almost identical. Those lines are going to be really overlapping because they are not that much different, because this normalization by dx already provides a really great normalization when we have enough of the x-axis sampling to get really, really close to 0. More generally, normalization is pretty tricky in statistics. It's tricky in machine learning, signal processing. Basically, anytime you're working with data, you're almost certainly going to have to deal with some kind of normalization issue. And the annoying thing, the confusing part about this is that different normalizations serve different purposes. They can give you different results, but this doesn't necessarily mean that different normalizations are correct or incorrect. They're just suited for different purposes. This is a theme that will come up over and over and over again throughout the rest of this book. Here we are in exercise 3 of chapter 8. This exercise is fairly straightforward in terms of coding, but it is important because it's really going to solidify, I hope it really solidifies for you this idea about normalization by dx to transform the output of these SciPy PDF functions into a real probability function. Okay, so what you want to do here is create 2 PDFs of a normal distribution, both having exactly the same x-axis boundaries, so going from minus 4 to plus 4, and both of them get normalized by dx. The difference is that one is going to have 100 linearly spaced points and the other with 1,000 linearly spaced points. So the SciPy function is the same, the boundaries are the same, the normalization is the same, everything is the same. The only thing that is different between these two functions that you will create is the grid spacing. So basically the x-axis resolution, 100 points or 1,000 points. Okay, and then you just plot them both like this, and I'm going to show you this in Python, and I'll have a small discussion about why these are so different from each other. I certainly hope that you did not struggle with the code for this exercise. It's pretty straightforward. In fact, inside this for loop over the number of points, and then I also have the different colors for the plot lines, is really just code that is literally copied and pasted from exercise 1 or exercise 2. So x-axis range, it goes from minus 4 to plus 4, and then I change the resolution according to the number of points. and then I compute the PDF normalized by dx and then plot it. And that's really all there is to it here. So the coding aspect is relatively straightforward. But it may be surprising. You might be surprised that the probability values are so different from each other. This one looks like it's just a little hill, and this is like a mountain in the Alps. Why are these values so different from each other, even though the probability generating function is exactly the same and the boundaries are the same? Well, the answer is that we are slicing up the x-axis grid into a finer number of points here with this line over here, with this function here. So, one way to think about it is imagine you have two dice. One die has 6 sides and the other one has 12 sides. What is the probability of rolling a 1? Well, the probability of rolling a 1 in a 6-sided die is around 16%, and the probability of rolling a 1 on a 12-sided die is a little over 8%. So, you could ask the same question. Why do you have such different probability values of the same exact outcome? So the outcome is the same. We're rolling a die. The key difference is that the 12-sided die just has more sides. So there's more probabilities of other events happening. Likewise, here, the probability of getting a value of 0 or, somewhere in the near vicinity of 0, it's the same outcome here and here. But here, there's just fewer opportunities. You cannot get a value in between this bin and this, or this number and this number, because there is nothing in between those numbers. We haven't measured the x-axis grid that finely. Here, when the resolution is higher, there's just many more opportunities for many different possible values for the PDF to have. So I think the conclusion from these first 3 exercises, this video and the past 2 videos, is that normalization is tricky in probability functions and elsewhere. And there's never really a right or wrong. You just have to be mindful that different kinds of normalizations, and also here different resolutions or data sampling, is going to have an impact on the numerical values that you obtain from these probability functions. Welcome to exercise 4 of chapter 8. So we spent the past few exercises on PDFs, and now we are going to switch to CDFs. And again, with this business of normalization and the output of the SciPy functions that generate CDFs. Okay, so in the book text, I claim that a CDF is the cumulative sum of a PDF. That's not just my claim. That's literally the definition of a CDF. But the question is, how do we normalize the CDF in Python? Do we need to normalize it? Now, you can already guess from the previous exercises that if we just cumulatively sum over the raw PDF, the raw output from stats.norm.pdf or any other probability function, it's not going to be correct, because those values themselves sum to, for example, 50. So then the cumulative sum is obviously going to be larger than 1. Okay, so what you want to do in this exercise is create an x-axis grid that goes from -4 to +4 in 300 steps. And then use that to create a CDF. Actually, you want to create 2 CDFs. One CDF you generate by taking the cumulative sum of the normal distribution. So get a normal PDF and do not normalize the output, and then take the cumulative sum, and we'll call that a CDF, or maybe give it a different name. It won't be a true CDF, as you will discover, but do that, and then use the output of the stats.norm.cdf function. Okay, and then make a plot that looks something like this. Let's see. So here we are looking at the PDF for the Gaussian. You can see it goes from -4 to +4, and these are the raw output units of the function. So this is not a true probability function. It would need to be normalized, but that's not what we are doing here. Here, what you see in panel B are the 2 CDFs that you should create. So the dashed line here is the cumulative sum of this function here. Literally just, each value is the sum of all the previous values. And then we have the output of the SciPy CDF function from the normal distribution. Now, you can already tell from the units here that, this should go up to 1. It should have a maximum value of 1, which it clearly doesn't. So that's wrong. But you won't be surprised about that because we already know that this needs a normalization. Okay, it looks like the output of the SciPy function is flat. This looks like a flat line. It's actually not a flat line. This is appropriately scaled. It goes up to a value of 1, but just with this y-axis scaling, you really don't see what's going on down here. Okay, so then that leads us to the next part of this exercise, which is to create the cumulative sum of this function again, but normalizing by dx, which you now know how to do from the previous few exercises. And then you'll see they overlap pretty nicely, the cumulative sum of the PDF and the raw output from the SciPy CDF function. Okay, so now I will switch to Python. I'll have a few more things to say about these functions, but I'll do that when I produce the code, or when I produce these figures in Python. After having gone through the code for the previous several exercises, I hope that you will find the code here to be relatively straightforward, which allows you to focus more on the important concepts. Okay, so here is the x-axis grid -4 to +4 in 300 steps. This is our raw PDF output, so the non-normalized PDF output, which we then take the cumulative sum over to get a CDF. And here I call this I don't know why. I could have called this NumPy or something. Anyway, and then here is the SciPy CDF. So this is stats.norm.cdf. Now, I would also like to point out the parallel between these two function calls. So we have stats.norm.pdf, stats.norm.cdf. In general, a lot of these statistics library functions work the same way. So it's going to be scipy.stats and then the name of the distribution, norm, x norm, f, t. There's going to be lots of different probability functions that we will be working with throughout this book. And then it's going to be .pdf or .cdf. And you'll see other methods as well later. But I just want you to see this parallel. It's going to work for lots of different kinds of distributions. Okay, so now notice that here we are not normalizing anything. We're not normalizing this by unit norm, by the sum, by dx. We're not normalizing by anything. This is just the raw output of the CDF function. Okay, so then let's see. This plot isn't so interesting. Yeah, this one is more interesting. And here now I am recomputing. So let me see. That is exactly equal to this line, but with the dx normalization that you learned about in the previous few videos. Okay, so now let's have a look at these graphs. So this one's not so interesting. This is the raw PDF. These two I showed before. So now the key take-home message here is that when we normalize the PDF and take its cumulative sum, that gives us the true CDF. You can see that it has a maximum value of 1, which is part of the definition of a CDF. So it goes up to 1. That's clearly not the case here when we take the cumulative sum of the raw PDF output. Now, so that part is not so surprising. The surprising thing is why the output of the CDF function from SciPy does not require any normalization. Why do we not need to normalize this gray line here? By the way, here you can see, so this gray line here, which looks like a flat line, it appears to be a flat line. You see, it's exactly the same function I'm plotting here, exactly the same variable, but just the y-axis scaling makes it look flat here, but it's actually not. It's going from 0 up to 1. Okay, so the question is, why do we not need to normalize the output of the CDF function? And the answer has to do with how PDFs and CDFs are calculated. So to estimate a PDF, true probability density function, we need to have a range. It is not possible to define an integral, a probability function, a probability density at one exact numerical value, like the value 1. It just doesn't exist. That's just not the way integrals work. Instead, to compute an integral, you have to sum over or integrate over at least some small range. The range doesn't have to be huge. It doesn't always have to be minus infinity to plus infinity. But for example, you can compute the probability between 0 and 0.001. But somehow you need to have a range of values to estimate a probability over. When we use the PDF function, we don't actually know, or Python doesn't actually know what the range is. So it cannot give a true probability density value without knowing the dx, without knowing the x-axis spacing. On the other hand, a CDF is not computed in the same way. CDF is computed as the sum of all the values to the left of that value. So we can compute the CDF of exactly 1, not a range around 1, but the exact value of x equals 1, because it's the integral from minus infinity up to 1. And that is the exact value. So that is the reason why you do not need to normalize the output of the the output of the SciPy CDF routines. Now, it is the case that you sometimes need to figure out appropriate ways to normalize empirical CDFs, and that is the topic of the next couple of exercises. This is the video for exercise 5 of chapter 8, but I actually want to start by going back to the figure from exercise 4. Now, if you look down at the panel C, you might see, I claimed that these two were the same and that they were overlapping. Now, that is kind of true. If you're squinting your eyes and you look quickly and then you glance away, it does seem like these are the same. But if you look really carefully, you might start to get suspicious. Maybe you're starting to think that these are not really identical. They are just close to each other. They're certainly a lot closer to each other than with the non-normalized PDF in panel B. But yeah, I mean, it kind of looks like the empirical CDF, so the cumulative sum over the PDF, even with the normalized PDF, it's a little bit larger. It looks like the values are a little bit higher compared to the output of SciPy's CDF function. Now, that is not just a weird thing with plotting. It actually is the case that these two functions are close, but they are not identical. And that leads me to the instructions for exercise 5. So basically, the goal of exercise 5 is to reproduce panel C. So that is the simultaneous plotting of the cumulative sum of a PDF normalized by dx and the output, non-normalized output of a SciPy CDF function. Okay, so repeat that panel twice, reproduce that panel twice, the one we were just looking at in Python, but using a high resolution and a low resolution. So high resolution means 5,000 points between -4 and +4. Low resolution means only 50 points between -4 and +4. Again, all of the functions are exactly the same. The plotting is exactly the same. The only thing, the boundaries are exactly the same. Everything is exactly so. Okay, the plotting is slightly different because here I only use lines just because it would be so hard to see with markers. Here I actually added markers just to show you the differences. Okay, but otherwise, really the only key difference between these two panels is the number of points that you use in the linspace function between -4 and +4. Now here in this plot, they really do look identical. These two lines look identical. You cannot see any difference between them. They appear to be perfectly overlapping. Here, this is like painfully obvious that there is a difference here. So question is, why is there that difference and which one is more accurate? I'm going to talk about that in more depth after I show you the code and produce this figure in Python. Again, there is not much new coding to do for this exercise. You can just do a lot of copy pasting from previous exercises, which is great because that allows you to focus more on the concepts and less on the details of Python implementation. Okay, so yeah, it's nothing really fancy in terms of coding. Here I create the PDF using x-axis spacing of 5,000 or resolution of 5,000, and then I plot it. And then here it's exactly the same thing, except here say 20. That actually should be 50 based on the instructions in the figure. Okay, so let me run this code here. And actually, now that I see this, in the book figure, I definitely used 20 points. So that was a little error. It will be fixed in the book. You'll see this correctly. The same concept works for 20 points, but I think it looks a little bit clearer with 20 points. Okay, compared to 50 points. You do still see that there's divergence, but with 20 points, it's really super clear. Okay, so what is the deal? What's going on here? The deal is that the SciPy function, here, the gray line, this is more accurate. This is the one you should use whenever possible, because SciPy is actually evaluating the true CDF function as opposed to our empirical estimate, which depends on the grid spacing. So you already saw from previous exercises that the grid spacing can introduce some numerical inaccuracies, and just some summation issues that are that give us a good approximation to a true PDF, but are not going to be really a true probability density function. It's just a digitized, reduced resolution estimate of a density function, and that's why it's called a distribution function. Okay, so basically, the black line is less accurate because it is an empirical estimate of a PDF that is based on a low resolution grid spacing, whereas the Python function CDF is actually implementing the direct CDF formula, the true CDF formula, which is the integral over all the values from minus infinity to each of these points here. Now, that said, it is not always trivially possible to use a CDF function that comes with SciPy, because you will, you may encounter situations where you want to compute a CDF of a probability function that does not come from an analytic formula. It comes from some empirical probability function. Maybe it comes from measuring data in the real world. So there is no SciPy function that you can use for that CDF. And that is something we will explore in the next exercise. Welcome to exercise 6 of chapter 8. Here we are going to continue exploring the concept of creating CDFs from PDFs, but this time it's going to be an empirical PDF. So it's not a PDF that's defined by a particular analytic function. So let me first show you the figure. So the goal of this exercise is basically to produce this figure and, of course, also understand all the concepts behind making this figure. So what you're going to do is start by creating a PDF that looks like this. Now, this does not come from a particular Python function. It's actually the sum of two PDFs. You can see it's two Gaussians. And I've just shifted one Gaussian. So here's one Gaussian and here's the other Gaussian. I will explain in a moment how to create these, but for now, just suffice it to say that it's the sum of two Gaussians. This is our empirical PDF. Maybe these are from data that we measured in the real world. Okay, so then what I want you to do is try to generate a CDF as the cumulative sum of this PDF, but normalized by dx. So you generate this PDF. This is in the raw units here. This is non-normalized, but normalize this PDF by dx and then compute the CDF. Now, that should be, you learned in the previous exercise that should be a really, really close approximation to the true CDF. But it seems not to be the case. In fact, the CDF needs to sum to 1 at the very end. So the final value needs to be 1 or, something very, very, very close to 1. But it's not. It's closer to 2. So then what you need to do is figure out a way to properly normalize the CDF so that it behaves like a true CDF, such that it has a maximum value of 1 at the very end. That's what you see here. Okay, now there's a couple of different ways to normalize a CDF. I'm going to show you 2 ways in Python, but I encourage you to think of ways that you think would work to normalize this function here, which is the cumulative sum of this empirical PDF, so that we get a appropriately, properly normalized CDF. Okay, before switching to Python, I will just explain how I generated this function. It comes from, so let me see, x-axis grid spacing between -6 and +6 using 1001 points. So 1001 linearly spaced numbers between -6 and +6. Then you want to generate two normal PDFs, two Gaussian PDFs, but you shift the x variable inside the PDF function. So one is shifted by -0.27 and the other one is shifted by +0.27. And the only thing that that's doing is shifting the Gaussian PDFs on the x-axis. So you can see this has a peak at -0.27. This has a peak at +2.27. So then you take these two Gaussian distributions, these two Gaussian PDFs, and you just sum them together, literally just sum them together. It's that simple. And that is how you create panel A. So everything else is up to you. I hope you enjoy working through this exercise. And now I'll switch to Python and show you my solution. So here you can see I create the x-axis variable going from -6 to +6 in 1001 steps. And then here is the sum of the two PDFs. So it's stats.norm.pdfx in both cases, but here it's x minus 2.7 and here it's x plus 2.7. And I call this variable PDF. Okay, so then I'm taking a cumulative sum, which should be the CDF, if the PDF is properly normalized, which I do here. So here I'm normalizing by dx. Now, this is a slightly different way of doing the dx estimation compared to what I showed in previous exercises. Remember, in previous exercises, I just said, the second point of x minus the first point of x. Here, I'm computing the difference, which is the discrete derivative, and then I'm taking the average of all of those differences between successive points. Now, this is unnecessary. It's a little overkill because by definition, from this linspace function, the distance between every 2 points is exactly the same. So we don't need to take all the differences and average them together. So partly the reason why I coded it this way is just to show you some variety, some coding implementation variety, and also just to show you, this actually does turn out to be a useful piece of code in certain applications. For example, in signal processing and time series analysis, it sometimes happens that if you are sampling data from a sensor over time, like an electrical sensor, a magnetic sensor, a sound sensor, sometimes the sampling over time is not exactly perfectly identical. And so therefore, the dx might actually change a tiny bit from step to step, from time point to time point. So in fact, in signal processing, this is a useful thing to know about for getting the average dx over the entire measurement. Okay, anyway, so then let's see, here I'm doing a couple of normalization. So one normalization I do is to, this is one normalization, the dx normalization, which you already saw from the figure is not an accurate, it doesn't give us an accurate CDF. Here's a different normalization, which you learned about in a previous video. This is the unit sum normalization. So here I am trivially forcing the sum over all the PDF values to be 1 by dividing by their sum, the sum of the raw values here. Okay, and then I take the cumulative sum here without doing any further normalization. So I'm not also normalizing by dx because we are normalizing the PDF first. Okay, and then I'll talk about this in a moment. Okay, so then we can look at the results. There's some plotting in there, and now we see the figure in the book. Now, what is the problem with this? Why didn't this work? This worked in previous exercises, normalizing the PDF by dx. The problem is that in those previous exercises, those PDFs were derived from an analytic formula for the Gaussian. Same concept for if you would get an F distribution, a T distribution, a chi-squared distribution, any kind of distribution that you get that is derived from a formula, from an analytic formula, there the dx normalization will work. But if you have an empirical probability function that comes from a combination of analytic formulas, or it comes from data that you've measured from the world, if you are estimating a probability function based on measured data, it's not going to look like an analytic function. So therefore, the dx is not guaranteed to work and will almost never work, basically. So then you need to apply an empirical normalization. Okay, so this one where we force the sum of all the probability values to be 1, that is one way to appropriately normalize the CDF. You can see the maximum value here is 1. Another normalization that you can do, which is also kind of trivial that it's going to work, is to, okay, this is not necessary to comment this out, but I'll do it anyway, just to guide your attention to this line. So here we know that at this point in the code, this is not going to be a properly normalized CDF, as we see in the plot. So what I'm doing here is just dividing by the final value of the CDF. And what this does is force the final value, so the last element in the CDF function is going to trivially have a value of 1. And that is another way of normalizing a CDF to ensure that the final value is going to be 1. Again, a theme that has come up in all of the exercises so far, which will come up again many times throughout this book, is that normalization can be tricky business. It's important to understand different ways of normalizing data and normalizing functions and normalizing distributions, because the different normalization methods can have important implications for the results that you will get from statistical analyses. Here we are with exercise 7 of chapter 8. This is one more exercise on CDFs and PDFs and normalizations. So the goal here is to demonstrate that a PDF can be computed as the derivative of a CDF. So that is the relationship between the PDF and the CDF, which I described in the main text of this chapter. So the CDF is the cumulative sum or the integral over the PDF, and that means that the PDF is the derivative or the discrete difference of the CDF. That actually comes from the fundamental law of calculus. I forget if it's the first fundamental law or the second fundamental law. Anyway, it is part of calculus that integration and differentiation are inverse operations from each other. So in the previous couple of videos, we were generating CDFs from PDFs, and now here we are going to generate a PDF from a CDF. Okay, so you want to start by creating a CDF of the log normal distribution using x-axis spacing from 0 to 10 in 200 steps. Now, a log normal distribution takes two parameters, the location and scale, and you can use values of 1 and 0.5. Actually, you can use whatever values you want, but if you use these two values, then you will reproduce exactly this figure that you see down here. But as always, I encourage you to explore different parameters if you like. Okay, so start by creating the CDF and generate a plot of that CDF, which you see here. And then you want to create two PDFs, one using stats.lognorm.pdf, and one by taking the derivative, which is on computers, it's the discrete difference of the CDF. So I hope that makes sense. So you get one PDF from a formula, from code, and another empirically by taking the derivative, the discrete derivative of the CDF. Okay, so then you want to make sure that you get a plot that looks like panel B. So you get the PDF from the CDF, so this is the empirical function, and this is from the SciPy lognorm.pdf function in dots. And then you want to make sure that you apply whatever normalizations you feel like you need to apply to get these to look identical. Now you can already see in this figure that these two functions do not look identical. They look quite similar, but not identical. So you can explore that on your own. I'm going to have a discussion about that when I generate this figure in Python. Here I have the x-axis spacing, which goes from 0 to 10 in 200 points. here is where I create the CDF using the function lognorm.cdf. So we input x and then the two parameters, location and scale. Okay, and then here I'm computing the empirical probability distribution function as the difference. So numpy.diff. And then, yeah, this is the computer approximation of the derivative. So if you're writing this out on the chalkboard, or if this were like a mathematical discussion of probability theory, this would be the CDF, which you define from integrals. And then here you take the derivative of that CDF. Okay, and then, yeah, here I'm calling this PDFD. The D is for the difference. That's what we are computing here. Okay, and then I have the analytic PDF that comes from lognorm.pdf. And here you see, again, this consistent parallel organization of these function names. So we have stats.lognorm.cdf, stats.lognorm.pdf. Exactly the same input parameters. That's important. If you use different parameters, then the results would be trivially different. Okay, and here I'm applying the dx normalization. So I'm taking the PDF, the analytic PDF, the output of this lognorm.pdf function, and just multiplying it by dx. Okay, and then generating the plots. And then you see that with that normalization, oops, I meant to do it. So yeah, let's run this with 200 points. And here you see, that there's a pretty good overlap. Certainly the amplitude scaling is the same in the two functions, these two ways of computing the PDF from the CDF or directly from the SciPy function. But you can see, as I noted in this comment here, it does look like there's a little bit of a mismatch. Let's see what we can do about that. Okay, so here I used 200 points, and so let's try 20, and I think you know what's going to happen here. So when we use a much coarser resolution, so we're sampling many fewer points on the x-axis grid, then you can see, oh God, it's painful to look at. It's so ugly. But clearly there's a huge mismatch. I mean, it sort of is consistent down here, but these values are very, very close to 0. So it's no surprise that numbers close to 0 are closely matched. In fact, I would guess, I'm not going to do this now, but if you like, you can try this. I would guess that if you would convert this into a logarithmic y-axis scale instead of a linear y-axis scale, you would see that actually the circles and the lines are still very far apart from each other over here. They just appear to be squished because the differences in terms of absolute numbers is small. Anyway, let's do it the opposite. Now let's do 2,000 points. So now we are sampling the x-axis grid at a much finer resolution. And here you see that the overlap appears basically perfect within my own visual acuity. This looks like a perfect overlap. Again, if you would zoom in here, you would see that it's not perfect. But the point is, the higher the resolution, the more accurate it's going to be. The more closely these two functions will match to each other. Welcome to the video corresponding to exercise 8 of chapter 8. Here we are going to focus on the difference between empirical probabilities and analytic probabilities. And in particular, an analytic probability never changes. It's defined by a formula or some equation or a theory, but it comes from some expression that doesn't change. In contrast, empirical probabilities can change as we sample data because they are coming from nature. They're coming from our measurements of the real world. Okay, so yeah, this is continuing along a discussion from earlier in this chapter about putting different colored marbles in a jar and randomly picking different marbles and what is the probability of picking a red marble or a green marble, it was yellow and wait, what were the colors again? It was blue, yellow, and orange marbles. Okay, there you go. Let's see. Okay, so the goal here in this exercise, you want to create a data set that simulates a bunch of marbles in a jar. So you want 40 blue marbles, 30 yellow marbles, and 20 orange marbles. So you can create this in a variety of ways. I recommend creating a NumPy array comprising 1s, 2s, and 3s. You can also use, 0s, 7s, and 114s. It doesn't really matter so much, but it is easy to use numbers. If you prefer, or if you want a little bit of an extra challenge, you can also complete this exercise not using numbers in a NumPy array, but instead using strings in a list. So you can have strings that say blue, the word BLUE, and yellow and orange and so on. So many ways you can solve this exercise. Okay, but the point is you want some object in Python that has 90 elements, and 40 of them correspond to blue marbles, 30 for yellow marbles, and 20 for orange marbles. Okay, so now we are going to simulate an experiment that models a real-world task where we are randomly picking a marble out of the jar. So imagine you have this jar full of colored marbles. You shake the jar so they all get mixed up. You turn away so you're not looking, and then reach in and pick out one marble at random, and you see what the color is. And then with that marble, you don't take it away. You actually put it back into the same jar. So it is possible to select the same exact marble multiple times from the jar. It's also possible to select 500 marbles, and one marble is never touched just because of random chance. Okay, so let's see. So repeat this random draw 500 times. And here I call it the sampling with replacement technique, but that's basically just what I described. So you pull out a marble from the jar, and then you record the color of that marble, and then you put the marble back in the jar. So that's the replacement. Okay, and then after doing this 500 times, you want to record the total number of blue marbles, the number of yellow marbles, and the number of orange marbles. Now we know, or you can compute, the analytic probability of selecting blue, yellow, and orange based on the numbers. Here, I'm providing these numbers. So the question is, how do the empirical probabilities of drawing these marbles of different colors from 500 random draws, how does that empirical probability function compared to the analytic probability function? And that you can graph using a bar plot with lines that look something like this. So here we have on the y-axis is the probability. We can also call this the proportion of marbles that we drew from each, the proportion of marbles of each color that we drew. I have a discussion in the text about the subtle but important distinction between proportion and probability. But anyway, here you see the black lines show the analytic probability, so calculated from math without actually without running any experiments. And then here in the orange bars, that shows the empirical probability, or the proportion of marbles from each color that were selected. So then it's interesting to rerun this multiple times and see if you get, a close match here. Like this appears to be really, really exact. Maybe this is very, very close. This is further away. Is there some bias in the experiment? We did something wrong, and we're always going to get more blue marbles and fewer yellow marbles. That is something you can investigate by rerunning this code multiple times. All right, so here I'm defining the numbers of marbles. So the total number of marbles is, the sum of all these three. Here's the way I implemented it. There's many ways to implement this kind of design. So I chose to use numpy.ones, and then I multiplied these vectors of ones by 1, 2, and 3. So this is going to give me 40 ones, and then 32s and 23s. Okay, now here's how I modeled this experiment. So we have 500 draws, 500 repetitions. And then what I do is pick a random integer corresponding to the length of the jar. So I implemented this by generating a uniform random number between 0 and 1 and scaling that up to 90, the total number of elements in the jar, and then basically rounding it by also taking the converting it into int. Now there's when I have code like this, I always get questions from students. Why didn't you code it this way? Why didn't you use the choice function? Why didn't you use this other function? And the answer is there's no particular reason. Sometimes there are reasons to prefer one method over another method, but very, very often in Python, there are multiple ways to solve the same problem. Sometimes it comes down to a matter of personal preference. Sometimes I like to code things in different ways just to give you some options and variety. But anyway, so here's the random marble. Now this variable here, this is actually not a marble. This is an index into the the variable jar, which actually does contain all the marbles. So you can see I'm picking a random index. Now this is going to implement random sampling with replacement because, I could get the same random number every multiple times. Okay, now this is not necessarily the best way to, or the most computationally efficient way to code this experiment, but I like this code, especially for learning, for educational purposes, because this is kind of how you would do it in the real world, right? In the real world, if you're doing this experiment, you have something like a for loop in your head where you keep, randomly reaching into the jar and then recording the color of that marble. And then you go to the next iteration of the for loop. Okay, so I hope this is extremely clear how this maps onto the experiment that we want to run. In practice, code like this is more efficient. This does exactly the same thing as all of these lines of code here, just in one convenient line of code. The important thing, if you're using numpy.random.choice, is to make sure you are setting this parameter appropriately. Replace equals true, which means we are sampling with replacement. Or if you would set replace to be false, that means we are not sampling with replacement. So if this were false, like this, it would mean that every time we reach into the jar, pull out a marble, then we put that marble aside and we don't put it back into the jar. So that is not what we want. Okay, the rest of this is pretty straightforward. Here I'm summing up the number of times that the marble equaled 1 versus 2 versus 3 divided by the total number of draws. Okay, and then, just some plotting here. Okay, so now we see that, it looks reasonably close. Some mismatch. We can rerun this multiple times. You'll see sometimes it looks closer, sometimes it's a little bit further away. So there is some chance, there is some randomness that is involved in computing empirical proportions or empirical probabilities. That is a concept that we will explore in the next exercise. Welcome to exercise 9 of chapter 8. This exercise follows closely from the previous exercise, so make sure you have solved exercise 8 before trying to solve this exercise. Partly that is conceptual, we're working with the same jar of colored marbles, but partly it's also practical. The best way to solve this exercise is to copy and paste a bunch of code from the previous exercise. Okay, so at the end of the previous exercise, we saw that by rerunning the simulated experiment multiple times, the empirical proportions and the analytic probabilities were kind of close, but sort of bouncing around. And so what we are going to do in this exercise is explore this concept in more detail, in particular by varying the sample size. So let's see. I hope you have a sense. Let me scroll back up to this figure. So here we saw mismatch. Here we drew 500 marbles at random. Now you can imagine if we drew, let's say, 3 marbles at random, we would not expect the empirical proportions and the analytic probabilities to be super closely matched. But if we drew 1,000,000 marbles at random, I hope you have the intuition that the bars and the lines should be closer together the higher the sample size. Okay, so that's like the basis for this exercise here. So this is also an introduction to the law of large numbers, which is an important concept in statistics. I'm going to talk more about it in the next chapter, but we'll have a nice intro to it here. Okay, so what we're going to do is compare the closeness or the match between the probabilities and the empirical proportion. And I suggest we do that using this quantity here called root mean square. Very simple formula. It's very often used in statistics and machine learning and signal processing, image processing, to compare two objects, two things that are similar to each other. So we have the thing that we want to compare. So the distance between, here I call it pi and p hat I. So this is going to be the empirical proportion and the probability, the analytic probability. So their difference squared, sum over all of the categories. So in this case, there are 3 categories for the 3 colors of marbles, and then we take the square root of that. So root mean square. So you first square, and then you take the mean, and then you take the square root. Pretty straightforward. You can imagine that the smaller the RMS value, the closer the match between the probabilities and the proportions. So for example, if the probabilities and proportions were the same, then their difference is 0, and then we get an RMS of 0. So that's kind of the ideal result. An RMS of 0 would be a perfect match. All right, perfect consistency. Okay, let's see. So then what you want to do is run an experiment where you take the code from the previous exercise, put it in a for loop where you vary the sample size from 20 to 2000. So in the previous exercise, we used a sample size of 500. Now you want to use varying sample sizes. So you draw 20 marbles, record the different colors, and then compute the RMS, and then in steps of 10. So the next one would be a sample size of 30, then a sample size of 40, and so on. And then you compute and store the RMS for each sample size and generate a plot that looks like this. So here is the RMS. Again, smaller numbers closer to 0 are better. That means a closer match between the analytic probability function and the empirical proportion function. And here we see the sample sizes. I'm going to say a few words about this, have a discussion about what this means, what its implications are for statistics, but I will talk about that after generating that plot in Python. So there isn't a lot of new code for this exercise. You will recognize this code. In fact, I probably didn't even need to rewrite this because I already had it from the previous exercise, but it's here again. Oh yeah, no. I put this in here intentionally to allow you to easily continue exploring the code for this exercise. For example, if you want to try to change the design, so change the number of marbles in the jar. For example, maybe multiply them all by 10 or something. Okay, but I will leave this as it is for now. So here I specify the sample sizes. These are the true probabilities. So it's just the true number of marbles of each color divided by the total marbles. Here is the key experiment. So here we draw our sample size. You can see now the sample size is changing, right? In the previous exercise, this was fixed. It was hard-coded to 500. Here, this n is varying with each iteration inside this for loop. And then here I compute the empirical proportions. This is the same code as I used in the previous exercise, just that in the previous exercise, it was 3 separate lines of code. Here I put it into a for loop. Okay, and then here you can see the sum of the RMS. So we take the difference, and then we square that. We take their average, which is the same thing as summing, dividing by n, and then the square root. Okay, so here we go. Now we can see the plot again. This initially actually looks quite different from the figure I showed in the book, but that's because we have a couple of outliers here that are pulling up the RMS values. In fact, this range here is really comparable to the figure in the book. Anyway, this is the nature of random having random numbers in your code that you're going to get different answers every time you rerun it. I'm actually a big fan of that for learning about statistics for reasons that I explain in the beginning of this textbook. Anyway, so a number of interesting things I would like to comment here. One, you do see that the RMS decreases with increasing sample size, but that's mostly driven by really large RMSs at the very beginning. There isn't a lot of decrease. I think if you would fit a line, you would find, even excluding these outliers in the beginning, I think you would still find a significant decrease in RMS with increasing sample size, but it's not such a huge effect, right? I mean, you might have anticipated that with a sample size of 2,000 marbles, and remember, there's only 90 marbles in the jar. So when we sample 2,000 times, we are getting the same marbles multiple times. We're oversampling from this jar of marbles. Even with 2,000 samples, we're still not getting an RMS of 0. And in fact, sometimes you have RMS of small sample sizes. Maybe this is like 150, this value around here. The RMS can be smaller than a sample size with 1,900. So it's a huge difference in sample size. And purely by chance, sometimes we get a closer match between the empirical proportion and the true probability. Now, there are a number of things that you can play around with here that I encourage you to explore. You can try increasing the sample size even more, maybe go up to 100,000. Now, if you're going to go up that high, you want to skip by more than 10. Otherwise, this is going to take forever. You can also try, as I mentioned a moment ago, increasing the total number of marbles in the jar. So instead of 40, 30, and 20 marbles, make it 400, 300, and 200, something like that. But you're always going to find that the RMS values are kind of bopping around a little bit. They do get closer to zero eventually, but they're never perfectly zero. That is a really important concept in statistics because this is simulating real world data. We are sampling from the real world. And even in this small population, in this example experiment, the population is 90. There's only 90 marbles in the entire population. And we still, even with oversampling 2,000 times, we still cannot get a perfect empirical match between what we measure and what we know is the ground truth. And that is dismaying. It's sometimes a little frustrating about science in general, because it's just very hard to measure the real world with perfect accuracy. But that is a primary motivation for inferential statistics and starting to work with p-values, f-values, t-values, correlation coefficient, p-values, and so on. Anyway, I hope you found this exercise to be interesting and thought-provoking. Welcome to exercise 10 of chapter 8. This exercise is going back to CDFs, cumulative distribution functions, and here we are going to compute one empirically. This is going to be also a gentle introduction to the concept of p-values, which you will learn much more about later in the book. Obviously, p-values are central to inferential statistics, and you can't do statistics without using p-values, so it's really important to understand p-values. So this is a nice gentle introduction into the concept and computation of p-values. Okay, so generate 1,000 data points randomly sampled from a normal distribution. Now, this is not an analytic distribution that you generate. You are going to be sampling random numbers from a Gaussian distribution. Okay, so let's call that variable x. And then you want to have a vector of 41 numbers linearly spaced between -3 and +3. These are going to form boundaries. Now, you've used code like this before, or you've explored concepts like this before with histograms. So with histograms, we have a bunch of data points randomly sampled from some distribution, and we come up with boundaries. And then with a histogram, we want to know how many data values are between, within each bin defined by the boundaries. So it's not exactly what we're doing here, but I want you to see the connection to histograms. Okay, so let's call this zeta. This is going to be this vector of numbers between -3 and +3. That's going to be called zeta. And then the goal of this exercise, I'll get into the details in a moment, but essentially the goal is to compute the probability, the number of data values that are above and below certain values of zeta. So let's think about this. So when zeta equals -3, what do we expect? How many of these data values do we expect to be below -3 and above -3? You don't have to, don't worry about exact numbers, calculating exact numbers. Just generally speaking, we would expect very, very few, if any, data points, maybe a few data points, to be less than -3. And we expect most of the data points to be above -3. Now we can think about the value of 0. So when zeta equals 0, what do we expect? We expect about half of these data points to be below zeta equals 0 and about half to be above zeta equals 0. And so on, we could think about +1. When zeta equals +1, we would expect more data values to be below zeta equals +1, but also, quite a significant minority of values to be above +1. Okay, that is the concept that we are going to quantify in this experiment. So in this exercise. So write code that loops through each value of zeta and compute the proportion of data values above each of these zeta values and the proportion of data values below each zeta value. Okay, So those two quantities is going to give you panel A here. So this is the bound for zeta. This is our numbers from -3 to +3. And the values here on the y-axis are the proportion of data points from our random sample, from our little data set, that are above zeta, that you can see here, and below zeta, and that you can see with the dark gray circles. So again, they cross around 0 because at 0, we expect around 50% of the data points to be above and below the threshold. And here at a threshold of -2, when we compute the proportion of data values below zeta equals -2, we expect that value to be small. It's going to be a couple of numbers, but relatively few. But when we flip the computation around, then we expect most of the values to be above -2. Okay, so these are one-sided proportions, right? It's greater than or less than the boundaries. Then what you want to do, also inside this same for loop, is compute the two-sided proportion. So there we are looking at the probability of the data value being greater than the absolute value of zeta. So that's essentially just the sum of these two. It's the combination of these two functions, and you can implement that as the proportion of x values, data values, that are greater than the absolute value of the threshold. And you see that this one kind of goes up and then it tapers down. Now, this is not a Gaussian function because it reflects a proportion of the data set that is more extreme than a particular threshold. That's not the same thing as the histogram of the data set. Okay, so I hope that all makes sense. When you learn about p-values in subsequent chapters, you can come back and think conceptually about this exercise, in particular these proportions, because this is conceptually similar to how we will compute and evaluate and interpret p-values. So here we are in the code. I'm generating 1,000 samples randomly drawn from a normal or a Gaussian distribution. Then I define the boundaries here. Here I parameterize this using k. And so k here is set to 41 because that's what I said in the exercise instructions. But yeah, now that you have this code, as always, I encourage you to explore, and you can try changing the sample size. What happens when the sample size gets small? That's pretty interesting to look at. What happens as k gets bigger or smaller? That's admittedly slightly less interesting to look at, but I shouldn't make judgments. You explore this on your own and determine for yourself whether it's interesting or not to make k relatively smaller or larger. Okay, let's see. So here is the key part of this exercise. So in a for loop over all of the different numerical values in this bounds vector, which is what I called zeta in the text, here I compute the sum of the data values that are greater than this threshold. So each value in this vector bounds divided by n, which is our total sample size. So essentially, this is the mean. I guess I could have also done the mean here and gotten rid of this. But so this is the total proportion of data values above the threshold and below the threshold. I store those in variables that I call empirical proportions greater than and empirical proportions less than. And then here's the two-tailed. That's basically the same code. You just take the absolute value of the bound instead of the signed value of the bound. All right, after that, it's just some plotting, and we can see the results over here, which look just like what I showed in the exercise text in the book. So you will learn in later chapters in this book that what we are doing here is basically computing the probability that the data value was larger than some particular reference value. And that is conceptually what we are looking at when we calculate p-values.